停水电话，但是打雷吧，但是那个它整个群的问题会
回转，请挤出话筒。
Okay, so let's start continue with modules. But then today we will consider a chain complex of modules. So how many of you like taken algebraic topology before? Or not about chain complexes? No, nothing. Okay, good. So then we will start fresh then. Okay. But then actually we see short exact sequence already again before in this course. If you maybe remember, maybe I can motivate from there. Short exact sequence. Okay. So anyone can recall what the short exact sequence is? So this is a short exact sequence of I think we call it modules. Okay, if phi is surjective and anyone remember? I think it's not as that direct, right? I think instead of they say it is injective, what is they say? They say did they use phi is injective? But definitely it's equivalent to this one. Or is it the subjective one is different? I think the textbook phrased it in a different way. Huh? What do you mean? So that we haven't introduced the chain complex yet. Sure. Oh, we introduced it for group last time, but then you can do it for modules also. So phi is injective, but phi is identified and with the kernel. Okay, so it's equivalent to say that phi is injective. So today we're going to say this short exact sequence in a different way, but equivalent way as well. Oh, for assignment, right? I'll try and finish it by before this holiday. Saturday. I just will give the thing. But assignment 2 I already released. Assignment 2, there are like 140 marks there. You just require to do, oh, there I forgot already. So you can pick and choose a question because these questions are actually quite variety. It's different kind of topics like algebra number theory or a little bit of algebraic geometry. So you can pick and choose which direction you want to go. If you want to do all, that's very good for you. Do it. Yeah. So if you do all, then we'll get the best mark for you. If not, you just do enough question. Okay. So phi is surjective. Okay, so we're gonna do this in a more general setting. So I'm gonna define what is a chain complex. Yes. And I will define it on R modules. Okay. So remember, a module structure is what? Is a abelian group plus a scalar multiplication. Okay, basically is that. You treat it as a homomorphism, right? You treat it as a homomorphism from the scalar field or the scalar ring to your abelian group. Okay, so this is the sequence of R modules and R module homomorphism. Okay, so we're not considering one homomorphism, we are considering a sequence of homomorphism. So we'll write it like, for example, mi plus 1 to mi equal to mi minus 1. So it's like m4, m3, m2, m1, m0, m minus 1. So usually these I should live in Z. Okay. And then the map, we label the map with the same number, same labeling of your module going out from the module that you had. Okay, such that for every I, ei compose ei plus 1 is 0. Okay, so you do the composition, you get 0. So if you do composition, you get 0, what do you mean? What does it mean by that? It means that the image of di plus 1 is in the kernel of di. Okay. So the image of di plus 1 is sometimes this number is decreasing, right? So decreasing meaning we are taking module homology. Okay, sometimes we call this a homology complex. Okay, because it's decreasing. So you could imagine that we can do increasing labeling. So instead of I minus 1, we can do I plus 1, I plus 2. Right? Huh? Yeah, sure. Okay, so these maps are what we call the boundary map. Or differential. Okay, maybe you think that these terms are very analysis or topology because exactly this object has come from there. Okay, it's boundary map. You can think of this mi plus 1, right, as a I plus 1 dimensional object. Okay, so you want to map a higher object to a lower dimensional object. For example, you want to map a line to a point. So what do? You send to that. Okay, then we can measure the this difference between the kernel and the image. So let's call the ith homology. So this is our definition of homology of the chain complex. Yeah, so note that this homology comes with a labeling. So it's important which thing is taken here. So you take this homology to be the kernel of di over the image of di. Okay, so meaning you take the kernel of di mod out by the image of di plus 1. Note that just now I already mentioned to you, right? Image of di plus 1 should be a subset of kernel of di. Okay, so this is measuring how much left after you pick up this image of di. So if what if okay, not if, never mind, unless it's a choice sequence, otherwise. But then you can imagine that they could be equal, right? So if image of di plus 1 equals to the kernel of di, then we will say that the complex is exact, exact at the MI. Okay. Because in that case, hash I m should be 0. 0 module. Okay. So if it is exact at every places, we'll call it as exact sequence. So just now, what we have is short exact sequence. It is exact if you go and show that this is equivalent to the kernel of psi and the image of phi is equal. And then similarly, you should add in the extra 0 map into it. Okay, show that the kernel of phi is equal to image of 0. And then kernel psi is equal to the image of phi. Then the kernel of 0 should be equal to the image of phi. Okay, why is it short? Because this is a 3-term complex. Okay, so you can imagine that this chain complex is like infinitely long, but then attached with 0 at the both end. Okay, but at those places it should be exact, right? Because it's just kernel of 0 man, image of 0 man. So they're the same. Okay. Does that make sense? Okay. Okay. So they are very this language is very convenient. Convenient in the sense that very convenient. Convenient in the sense that a complex. So if we look at an even shorter exact sequence, just maybe not shorter, but then starting with 0, okay, going to somewhere else. Okay, is exact at L if and only if alpha is a monomorphism. Okay, you can try and prove this. Very good exercise. So if we are in the category that injective makes sense, then these two might be the same thing. Monomorphism and injectivity. But in general, we have monomorphism. Second, obviously you can guess that if we have this exact sequence ending with 0, exact at yes, there you go, 1, exact at the end, you can show that it is actually a epimorphism. Yeah. Let me think. Abelian category. Okay, later we'll mention something called the abelian category. We want it to work So the abelian category he mentioned about is it is a category that where every monomorphism is a kernel. Does that have to do with injection? Injectivity? Then I gave you examples that monomorphism might not be injective, right? Or epimorphism might not be surjective. I'm not sure those are abelian category or not. Huh? What's the example? I think it's a example on integer. What should I search? Huh? 你记起来了？ integer I mean, we show that inset injectivity implies morphism and vice versa. But then but in module definitely true. Injective as a set function. Meaning it's not true as a module homomorphism. Anyone take this exercise? Injectivity as a set function. Yeah, I think it's not true in module also. Maybe it's just injective as a set function. But then set function can imply monomorphism. Yeah, anyone did this exercise? No. I think we should try this exercise. Okay. See what I can get for that. So maybe I keep the claim first and figure out. So maybe, so it's the claim. Is it true that, so maybe let me write down the claim. I think I'm reaching there, but then I haven't seen this thing yet. Huh? This is true? In the billion category? Is this true? You want to ask or you want to claim this is true? I try to prove this or disprove it. Yeah. 去想一下。Okay. Good question. Okay. Then what? Okay. Then this. So then we can rephrase our short as sequence in this term. So short as sequence is an exact complex, yeah, of the following form: 0 to L M. Okay. So you can try and prove equivalence between this and the one that you see in the group setting. There should be equivalent. Okay. So one thing you can see here actually, you can see here is n is isomorphic to m over the kernel of B. Okay, or it is m over the image of alpha. Because kernel of B is equal to the image of alpha. Is this easy to see? Is this easy to see? Huh? This is just another way to rephrase what you have spoken before. Like group ring module, you keep mentioning about this. If you have a surjective map, and then if you figure out the kernel, then the image modeled by the kernel is isomorphic to your domain. Okay. Yeah, this is basically it. Because this is the surjective map. Or epimorphism, right? Then this is the kernel. I mean, the image of this thing is the kernel. But then this image this is a what do you call it? This is the monomorphism, so it's surjective. Okay. Well, you have the canonical decomposition, right? Okay, so how do I write the canonical decomposition in this language here? So then if you have a module morphism, okay, then we get this Schwarzer sequence. Okay, so you can split your M into the kernel part and into the image part. Okay. I think we mentioned about split short as a sequence of group before split. When can we write this thing as a M as a direct sum of the two things? Okay. But then in general, you can do this because you will always have the injectivity here, right? Because the kernel is something you get from your module. And then you definitely subject into your image. Okay, and then the composition of these two men is zero because this is leaving the kernel of phi. So here is phi. And here is the inclusion. Okay, so by construction, it is exact. By construction. Because the kernel of this map is exactly the kernel. Then this one is injective, so you get exact. Then this one surjective, you get exact. Okay. I think in the module setting, okay, never mind. Okay. Next, well, if you have exact complexes, okay, if you have exact complexes, okay, so you can break this down into a number of short as a sequence actually. Okay, so meaning you attach what I did just now. Okay, so let's say this is di plus 2. Yes. Yeah, sorry. So you have you can continue it. But then I will show one part of it. Okay, so let's say I break it into like what I do just now. So here is the kernel of the I plus 1, and then here is the image of the I plus 1 as well. Okay, so I can break into like this. For this one, I also can break, right? Um, so here, let's say this is the kernel of the I plus 2, and then here is the image of the I plus 2. But then we know that it's exact, right? Exact means what? The image, okay, the kernel of the map is equal to the image of the previous map. So you can see that actually this two is the same. This two is the same. Okay, so instead, maybe we move it down. Okay, so let's move this up. Move the arrow a bit down here, such that this is equal to the image. At least, okay, so this two is equal. Okay, and then you can extend your 0. Okay, then similarly, you can do the same picture here. Same picture here. Let me see. Okay, my arrow is wrong here. Going down. Okay, you can do this picture. Good. Good. Okay, so this picture, if you have taken algebraic topology before, right, it's a bit like a cellular complex, or when you define a cellular complex. You also have a bunch of these choices sequence. Okay, good. Okay, next, we're going to discuss split as well. Okay, like what we did for the choices sequence for groups. So a short angle sequence, say to split. Okay, if there exists a commutative diagram of this. Okay, so meaning the chain complex will be um, isomorphic to the other chain complex. Chain complex such that the other chain complex contain a direct sum of module here. Okay. And then you want it to be commute. You want it to be commute. And then the vertical map should be isomorphism. Okay, I think I drew it already. Okay, you want it to be commute in every square. You know what commute means? No? Okay, so if you start at one point and at the other point, you can see that there's different root, right? So there should be end up should be the same map. So it's sufficient to check every box. Okay, once you check every box, then any box is true. And you can prove this actually. Okay, if you can check that every box, small box here works, it will work for larger box. You can try and show it. Okay, so you just check for any the small box. Okay, so what's the nice thing about this splitting language here? So similarly, we can rephrase this. Okay, so I mean, mathematics, right, is an art of rephrasing actually, giving things different name. So in this class in particular, we'll give a lot of name for the same thing. But actually you also see the advantage of doing these things, right? Okay, we can see things in a more general setting. Okay, we include more stuff to discuss. Okay, sometimes at the expense of missing out details, but then some feature we could collect them together. Yeah, this is the point of algebra. So we try to abstract things. Okay, we try to see the principle behind the things. Okay, yeah, does it make sense? Right. For example, monomorphism will work in more general case, right? But then injective might not work. Okay, yeah, yeah. Sorry, homomorphism, homo，怎么？我漏写了，我还没有写完其实。Okay, then we can say that phi has a left inverse if and only if the sequence of m to n to the co-kernel phi split. Okay, how do we define co-kernel? Anyone still remember? Hmm? So you take n multiplied by the image of this map. So this map is called phi. Okay, so you can think of it as if the thing does not get mapped by the image of phi. So co-kernel. Co-kernel. So it's the thing that cannot reach by phi. Yeah. Okay, so you send the image of phi to 0 in this quotient. Okay. Second. So that's why it calls co-kernel. It's like a kernel in the other sense. Okay, I don't know. You can try and interpret why do we call it co-kernel. Okay. Next, phi has a right inverse. Thus, if only if the sequence of 0 to curl phi to m to n split. Okay, so these two are dual statement, right? You can see that. This is what we call dual. One of them is changing direction, the other is changing some object to its dual object. So co-kernel and kernel. So let's do one of them. Okay, let's do maybe part one. Okay. Sorry. 哪一个 injective，哪一个 surjective？哦，okay, yeah, sure. Well, well, yeah, can try and think about it first. Yeah. But I think based on the exactness, right, that appears here, right, you should know what is injective, what is surjective. Because I think in a lower form, complex form, right, we'll ask you to prove that a map is if a map have left inverse, it is injective, or if it's right inverse, it is surjective, right? But also from this exact form, you should see, right, just now we proved that if you have an exactness at n, right, then you will have this map to be subjective, and in the other case, it's subjective. Depend on where you have exactness that connect to 0. Okay, one of them is going from 0 to that map, one of them is going from. Okay. Well, so what should we do here? So there are two directions to do, right? Okay, so show that if it has a left inverse, then it's split, and then show that if it's split, then it has a phi has a right inverse, left inverse. Okay. Well, so Because it's split, right? So that means what? What does it mean? Does it mean here? So you should have this split exact sequence here. Okay. Right. Okay, so it's split. If it is split, it isomorphic to some sequence that look like this. Okay, maybe we can try and think about it. So how does this splitting sequence looks like? I think did I put too many things here? Do we have this extra prime here? I feel like we just take this too. Otherwise, this one is too much. If I can show it with different MI. Let me think. I think it's fine because it's an isomorphism here anyway. I think it's fine, huh? I think it's fine because it's isomorphism anyway. Okay, never mind. Okay, so since it's split, so let's use shorthand notation. Since the complex split, so what do we have? Okay, we should split into something like this because it's isomorphic, right? Let me think. It's isomorphic. Can I replace with the identity thing? Okay, never mind. Let's say this is isomorphic to this, so this is, let's call it M prime. And then here is M prime prime. And here is also isomorphic. So here is M prime. Okay. But then we want to have a left inverse for phi. Left inverse means what? What does left inverse mean? I need to go where? I mean, like, maybe ask Pei. Yeah. What's the left inverse of phi means? Let's say this left inverse, I call it G. So I want G phi to be identity or phi G to be identity. Which one is left? A. G phi or phi G? Maybe let me write down. G phi is identity or phi G is identity? Which one? First or second? Huh? Choose one. You can only choose one. One or two. Two. So two is left or right? You multiply from the right. Okay, so this is what we call right inverse. So you have to pick one. Okay, so this is left because you multiply from the left. Okay, now. And 分得清 left right 吗？Okay, left multiplication, right multiplication. Okay, so you need to find something that when you post-compose, you get identity. Post-compose, right? So you need to get something from n back to m, n back to m. Okay. But then you know that n looks something like this, though. Okay. So you want to get to m, what do you do? Your n looks something like this. So what do you do? M actually is one of them, right? Huh? M is one of them, right? Okay, so you just project to this guy, then use isomorphism. Okay? So maybe let's call these isomorphism names. Let's call this. So we have this. We have okay. So now find G to be uh, doing psi one first. Okay, and then doing projection, project onto M prime. Okay, and then you compose with phi to inverse. Let's say this psi to inverse. So let's say this psi is going down, so you can go backward. Yeah. Do we need to check that? G psi G phi is identity. Is this easy to see? Is this easy to see? Huh? Project to M prime. Project to M prime. Because we regard this n as this direct sum. So I project to this point here. And then take this point back. What is the identity here? So you will n the identity. 因为你绕了个圈儿啊，绕了个圈。You mean? I know, but then this two thing, how do I know I go back to the same place? How do I know I go back to the same end? 啊，对。Yes, yes, yes. 啊，What do you mean? 所以你说 M embed 进 direct sub 跟 project 回来是反，然后对，所以你这么绕圈就回来了。怎么知道呢？来，OK，find some M 是一个东西啊，可能这个东西透过一个 map 去到这边，可能我只是看它的第一个 component，可能我回去了，我那知道为什么一定要回去同一个地方。因为那个方程不是同一个东西。好，没有然后对，应该是要用 computativity 的东西把它这样。Maybe we should try right now. What is this? Then Ah, I think I know. Wait. 来了。So using commutativity, what we should get here is this is 5, 2 on which one we do first? Okay, on the inclusion. Okay, so inclusion here we say I am prime. Okay, so I am prime on sine 2. Okay, but then if you include and project, what do you get? You should get identity. I don't know. You include and then project. So you include, okay. So you include here, maybe let's draw the map here. So here map. So here your M get include into M comma 0. Right? And then you project back is still M. Right? Agree? You inject, you include, and then you project back. X go to XY and then you project back to X. So it's identity. Then you compose sine 2 inverse and sine 2, you also get identity. Okay, no? Okay, so basically we are using commutativity here. So you can see how important this commutativity is. Here is the commutativity. Okay, does it make sense? Okay. Okay, so this is the business of chain complex. Basically, you can go up, go down, as long as you have isomorphism. Otherwise, you only have one direction. Okay. How about the other direction? So let's say if it has a left inverse, what's the uh, what's the um what's the what do you call that? What's the direct sum you should get? I don't know what am I copying from my textbook. I think we have to do also. Textbook. I think textbook explanation is very simple. They didn't do this tedious thing for you. They just tell you that the projection. They basically just tell you this map here. Okay, they didn't like go through this detail. Okay, so this is one direction. It's going from. How about left to right? So assume that split 去 left 嘛，又去左边 right to left，这样是 left to right。Assume that psi has a left inverse. Let's call it psi. Let's call it psi. Then, so this psi here, how do we record it? We can record it this way. So phi go from m to n, psi go to m to m, and then there's identity. Okay, use this commutative diagram to talk about it. Okay. So now maybe there's one very interesting tool you can use from now on. Whenever you see equation, think whether you can write it as a commutative diagram. Yeah. Okay, in particular, that relates these functions. Okay, it's pretty important. You can draw out their domain and column. And then with arrow, then you have a commutative vector. Okay. Right. Then how should we say that it's split? Well, I think the hardest one is just this one. I think this. Okay, this direct sum here. Because these two, I think, if this come out already, I think these two are quite straightforward. Okay, basically, what do you do? Why not just treat this as identity? identity definitely is a isomorphism. Okay, so maybe one thing left to show is can we show n isomorphic to M plus the co-kernel of phi? Okay. If this is done, then the inclusion projection is very easy, and then isomorphism is directly identity. Okay, and then to commute, okay, still depend on your isomorphism. Okay, but it should work out if it works. I hope. Okay. So let's try this. Then we just straight away define one map from n to m plus co-kernel of phi. Okay, how on earth we're going to do this? Well, you only have like condition for phi and psi, right? So you're going to use those, right? You're going to use those things. So maybe you think about this direct sum first. Okay, let's think about this direct sum first. What are we really doing here? What is m? What is co-kernel of phi like relative to n? What m supposingly to be? Okay, so if you look at this short exact sequence here, right, it's exact there. So exact there meaning what? Exact meaning the image, okay, image of phi is the kernel of phi is the image of this. So image of this zero map is zero. So the kernel here is zero. But then we want to know about what is m, right, relative to n. What is m here? M should be identified as a image of phi. Why? Because the kernel of phi, just now I argued to you that it's zero, right? So meaning nothing from M is get back to zero here. So M includes into N. Does it make sense? Yeah. So it's an inclusion. Okay. So let me draw this. So here, phi M is exactly. Okay, but then since it is exact, right? The kernel of N, right? Kernel of N should be, sorry, not kernel of N. Kernel of this map here, the next map. What should we call this? This is a quotient map, right? Okay, so this is the quotient. Maybe call it pi. And so this quotient map here has the kernel as the image of pi. Okay, so this is how we define it. Okay. Well, so we try to split this n into m part and the so let's do some in lower form we call it working, but then we try to think about what these two things could be. I mean, how to constitute this n here. So this co-kernel of phi, right, is n mod out by image of. Okay, but then we know that this m, right, is actually isomorphic to image of phi. Just now we say that m sit includes into n using this phi here. Okay. So co-kernel is exactly the rest of the n. Does it make sense? Can you imagine or not? These two things add together is n. Imagine. Huh? 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 Where do you use the map? I haven't defined the map. I need to produce you the map. I need to use those things to produce the map for you. And then show isomorphism. I won't tell you what this map is, but then I'm just trying to tell you that why this decomposition makes sense. Right. So one part is n take away image of m5. So what's left? to build your n. You need the image of 5, so you add it in. Okay. Make sense? Does it make sense first? Before we define the map. Okay. Okay, so now we're going to define the map. So what's the isomorphism here then? What's the isomorphism here? Okay, so you see, you need a map. If you want to go here to here, right? You need a map from n to m. Do you have a map from n to m here? It's exactly the map inverse. Try and use it. Let's try and use it. We're gonna show it. It is a invertible thing. Okay, and then how about the other one? Okay, so what are you doing here? You are taking one n. Okay, take your left inverse, send it to some n. Okay, so use the logic that I told you just now. Once you got this phi n, right, you need to figure out something left over plus something left over. So can you imagine what's left over here? I mean left over from n 啊，剩下的东西。Can you imagine or not? Can you imagine? Try imagine. Right. So you have n. Okay, you send it back to m. Okay, you send it back to m, and then what's left over? What could be the leftover? It must be some difference. And actually, you can take away phi psi n. Let's see if this makes sense or not. Let's see if this makes sense or not. So, what is kernel of phi? It should be something in n, right? Okay, so you need to make sure your map go back to n. If you had to use this domain, codomain way to think about it, also work first. You can guess first and then try and check. So you take n, so n going back to n already. Okay? And then you take away, what am I doing here? This is not an item potent. Okay, so you send it, you use the left inverse, send it to m, and then you use the map from m to n, I, okay, and then see what is it. Let's take the difference. And then we claim that this map is an isomorphism. Okay, so meaning there's a inverse. Okay, so what's the inverse here? Okay, so what's the inverse here? The inverse here turns out to be not too hard, though. Not too hard. Okay, so you need to set everything back to n, right? Okay, this k here is already something in n already. Okay, so you can send it to basically phi m plus k. Okay, you can try and check that this is an inverse. And then obviously, I think you need to check. I think from this side, you need to check well definers because you are defined on the quotient. Okay, from that side is okay. That side is okay. This side, I think you need to find show well definers because you are defining up from a quotient. Because let's say like k1 equals to k2, then would there be any problem here? Should we verify together or you can try? So, maybe we try one direction to see we are convinced or not. So let's go. Let's call this PQ. Let's do Q1P. Okay, I think I give you a different direction, is it? Can I give you a different direction? Is this a left or right 啊？做这个再做这个，最有这个 left 的对啊，OK。怎么我这个是反的？都理不是做不出来？哦，没有，我还没有写完，先揣揣看。嗯嗯嗯，M 放这边里面。
那反的才行，你不然你 sin 派不是就是 M。
等下，冷静一点，给我看一下。加 n 减 5，OK，good，OK，好，cancel 掉了，very good。OK，哎，OK，good。So you do the other way around. You check it. Everyone okay? I was just checking. QP is identity. You need to show PQ also identity. Okay. Why I got the feeling here is very weird. This like here. If it's well defined. How to show well defined here? Let's say if that one is different from the other by the image of phi. And I can think. Anyone is worried about this well defined or not? This one. Well defined. This part here. If this is a k plus the image of phi, right, then something is wrong. Huh? How do we fix that now? How about do the other direction? Let me see what's the calculation. So if I do PQ of MK, 对，我要看一下怎样把它变正常。P of 5m plus k, and then we get the sine of the whole thing, and then comma sine of m minus 5 sine m. Okay, so it's a left inverse, right? And then homomorphism, so we get this to be identity. So I got m, but then what is sine k? Because k is sine k. What's sine k here? Sine k. What's sine k here doing? Okay, let's skip this first, see how it works. Let's take away. So I get sine m again. And on one side I get minus 5 sine k. Sine k pop out again. Wait, let me see. So 多了一个东西。 A minus 5 sine k. Wait, why so weird one? So we want this to be m and k. So that means these two things have to disappear somehow. One side is okay, the other side got problem. So, but well, I mean, like, if you want to make this side, I mean, this k disappear, right? I think well, I mean, it should be something in the kernel of the side. 啊？什么？什么？算是写 kernel 啊，kernel 啊这个可能，这个是可能，这是可能，给我想一下，kernel of phi inverse，哦，kernel of 那个 sin，啊，这样 make sense，这样 make sense，but then 给我想一下，给我想一下，什么阅读可能 sin，给我想一下，but then subjective，kernel 就 make sense，确实 kernel make sense，嗯，啊，对对对对对，kernel 就不要解决，对对。But then 哦，我有一个问题是，我这样把可能装在这边。哦，可能 of sin，它是可能 of sin。想一下，可能 of sin 跟 co 可能 of phi，我就写一下。OK，so 如果把这个改成可能 of sin 就解决了。sin，连这两个 term 就零了，对不对？But then，so OK，这样的话要解决那个 split 的问题了。So what is split？嗯，and 去到 co 可能。这个是塞呀，想一下，怎么会 isomorphic 啊？不要跟我讲要用什么那个 phi lemma 的东西吧？What the fuck？是可以用 phi lemma 的，but then 什么？就这个这边两个那边不是中间那个，只要有两个 isomorphism 就可以去到第三个。Anyone heard of phi lemma before? No。如果没有的话，我们也要直接证吧，I guess。这样的话，可能是要用那一个诶。I think you cannot see from the definition. Can you? Can you see that co-kernel of phi and psi is isomorphic?
但你有这个其实就是它就是说可能反
Yeah, yeah, yeah. 对，
用不了反来嘛。
它是中间那个啊，我可以把后面两个看成 isomorphic，后面两个是零零啊，这边啊，这边两个零零，five lemma，five lemma，反正就是两个就有一个啊，反正。So should we use the homological algebra true or can we directly see on co-kernel? Kernel. From this picture, can we see it? 我觉得也不要那么复杂，很烦欸，我不要去那边欸。Let me try this。还是我们要用 universal property？好烦哦，
我觉得你从 F 1出来就把这个是
好烦啊，好烦啊，好像要用 universal property。kernel of phi，and then 这边装一个 kernel of sin，然后我们要有一个 map，这样子。我们有没有 universal property 啊？I think 我们有不是 universal property of kernel 有不是？Right. So let me think. 就是那个 check 一下几点了？还是我们 break 先？我去找一找。Okay, let's break until 3:30. 配仪的那个部分是不是？配仪有讲过。可能 OK。呀，这边，没必要用这个东西吧？可能。哦，是箭头不太对啊，哦，是线的，箭头好像不太对。这线是不对。unless 我的扣可能要进去的地方，扣可能还是扣可能的 definition 呢？扣可能是 initial。嗯，哎，我好像去错地方了，是不是？可能 of phi 是从 phi 是 m，so I guess I think kernel of phi I can put here. Then then MNP MNP 可能这是可能我发的对啊，很想画一个箭头过来哦，画得到吗？这个箭头啊，我要解释啊，不得，这个箭头我有没有？不对呀、因为如果你要用 universal property 的话，应该是两个都要往进来，或者两个都要出去。 OK， 一个几个处。OK， 我再想一下，说 co-kernel 是 n 切掉 image of psi 的话是 kernel of psi， 这两个组在里面是一样的。好看。Can we straight away produce this? Okay, I think to produce this, right? I think we want to use the what do you call that? First isomorphism theorem. Right. So if you can produce a surjective map right from N to curve phi and then show that its kernel is image of phi, then you are good. So I think now is to produce a surjective map. Yes. Yeah, that surjective map is because this is module, right? Okay, because this is module, we can split this N into kernel of psi plus image of psi. Okay, this is module. 为什么啊 module? Okay, maybe I think maybe one exercise you can do here. Huh? Exercise, I think this sequence here split. I guess at least for finite dimension, okay. For infinite one, I think also split. I think this was split. This just split into this. Or should we prove this? This decomposition here. This one, I think okay, right? This map here, is it hard? You basically you send M to one side is 5M, the other side is what's the color? Phi kernel of phi should be something living in M, right? Let me see, do we have any more condition? No more condition, just one. Just always split or not? Okay. I think when it is not split, it's infinite case. Yes. If we cannot have splitting, then it's pretty hard. If not, then we need to rely on the abstract nonsense. Yeah. 哪里？这个为什么要换去 kernel of V？为什么哈？Because if you go through this calculation, right, we have some extra thing when you do the other direction. But then this extra thing, right, can disappear if k is the kernel of psi. Does that make sense? 你说这你要换 map 哈？你要换 map？我define 那个n 减 yeah 是什么来的？
我们去看一下这个 image 是不是就是 image of？
谁？
我严重怀疑，就你右边的那个
，yeah，
就那个 n 减 phi psi n 吗
yeah，
严重怀疑它的 image 就是 phi，所以不是 phi 什么。
image 跟 phi，
我严重怀疑它的不是，就是它的 kernel 应该就是 image phi。你可以检查这个 map 的 kernel 是不是 image。
你说那个东西活在 image of phi？
不是，是那个东西的 kernel 就是 image of phi 了，就变成三方往六边。
你是说？这三公决定。喂，现在要做梦，我不明白你讲了。你讲我不知道你讲。
让你去确认一下，就是。
这一次我你可能有骗。也为了弄掉那个两边。因为我就是看剩下的东西。
这个
剩下的东西，
这个东西已经是一个从 n 去到 kernel of psi 的一个什么东西的。
也没错。
所以如果我们接下来的话，我们可以去试试看，说一个去修这个 map 是 subjective， 然后再去修它的这个 map 的 kernel 就是 image of 这个东西，然后这个 map 的 image 就是 kernel of 这个东西，然后我们就可以修 for psi。
你是说它是没有啊？你说它 injecting subjective 吗？
但是我的意思是去修这个 homomorphism 的 kernel 就是这个获取掉的 image phi 就可以。
但是你也是要 rely on 那个 n 切那个 phi 的。isomorphic to m 的话，可以 prove 到 n isomorphic to m plus。这个东西我们也没有分过的。
哪都没有。
是。你的意思是说，这个 imply 这个对吧？
不是啊，
不是，
我
让你讲用分。
是叫你直接用 for psi
然后还是你是说它的 kernel 是0？
不然让你去修它的 kernel 的 image of phi。
对呀，我现在就是要做这个 map 啊，但是我so you are saying that okay well I mean like 我看一下对 yeah so I think my problem now is how to define n to kernel kernel
我觉得可以啊，就直接用 for psi 方，这样就可以，就这个东西。
对，我是说
来你刚刚定义的那个 map 从 n 去到
you mean use that map？
对，就是那个 map 可以的，
可以的，真的可以。
我差 subjective， 但是我已经知道它的那个 kernel 很，它的 kernel 就是 image of n， 它的 kernel 就是 image of phi，然后就只要去修这个 derivative 就可以了。我现在。
Okay, so maybe look at this map here. Okay, look at this map. So why is this? What's the kernel of this map?
这个的 kernel 就是那个就是 image of phi，然后你去用那个两边 inclusion 就可以行。
Kernel of P is all the n in n such that n in n such that n minus v phi n equals to 0.
我 claim 这个东西就是 image of，
which implies that phi psi n is n. 对，
那么首先这个东西已经是 contain 在 image of。
So first of all，
首先这个 kernel 已经活在 image of phi 里。
等一下，我看一下 image phi。OK， image of phi，
因为你 n 是等于 phi psi n 嘛，所以这个 kernel of p 一定是 contain 在 image of phi 里面。
Let me think. Oh yeah, right.
然后
So wait first. So kernel of P should be a subset of image of phi because
cos n 等于
phi n is the pre-image of n. How about the other direction?
其他的代号系你就取一个 phi image phi 里面的 element。
Also phi n. Oh, sorry. Also image of phi is in kernel of P because
取个里面的 element。
because
let n 等于 phi k， 然后你代入你就会发现
consider a equals to phi of something.
the n equal to phi。
Okay, for the n equals to phi of psi k, where k is in n, then phi psi n equals to phi psi phi k, which is phi k, which is n. Yeah.
问题还是下一个 surjectivity 要去。
Yeah. How about surjectivity? So everything in the kernel of psi have to be can be found surjective, meaning there exists an n such that this is true. This is surjective. Anything that satisfies this okay, so maybe just write it down. Suppose x is in curve phi, the sign, then sin x equals to 0. This is what we know. Then you just text n equal to x. So,
哦，是。
huh? So
等于 x， 所以就
so take that x minus phi psi x is x. Okay. Yeah, then use first isomorphism. Okay, so we don't use the 5 lemma thing. Okay, so it turns out that this map is the isomorphism that relate curl phi and call phi. Okay, so isn't it? I didn't say that you cannot use call phi. It's just that we apply an isomorphism. Okay, this isomorphism will make life easier, a lot easier. Okay, good. Question? Go question. Okay. Maybe you can ask a question. How do I come up with this map? How one can come up with this map? Maybe you can ask this question. How one can come up with this map? Okay. So remember that this direct sum is some sort of difference. 2 plus 2 is equals to 4. So what is the 2 there sitting there? 4 minus 2 is 2. Is the difference. Okay. So you need to add the difference, the leftover. Okay, you need to add the leftover. We need to build the whole thing.
你好像用过 P 的，建议你如果写更高的，
我哪里有 P？ 哦，好吧，太多 map 了。要用什么呢？用 Z， 不要 Z 不好。用 OK， good， 很好，很好。Okay, next, this one is kind of exciting. The whole category theory business or categorification is about this Euler characteristic, point correct polynomial, or somehow we call it the quadratic group. Yes. Yeah. So this is the place where we play around with category. I mean, at least categorification. So categorification, so we make the category theory into a verb. So we try to put higher structure objects onto the lower structure objects. So let's define this first, and then I will tell you a bit more. So first of all, we let U to V to W as a short exact sequence of a finite dimensional vector space. CARE. Yeah. Point correct. Okay, shows a sequence of finite dimensional vector space. Okay, from here, definitely split. So we know that dim of V is equals to dim of U plus dim of W. Okay, so finite dimensional definitely split because you can write down everything in basis. Okay, so then you will have a basis for your kernel, you have a basis for your image, and you split them up. That's the split you have. For infinite case, there will be some weird thing could happen maybe. Okay. But then for finite dimensional case, you will always split. Or equivalently, dim of V over U is equals to the dim V minus dim U. Dim V over U. Okay. Minus dim V. This one U, this one. Okay. So this one very weird. This one is U V. Okay, good. This one need to prove or not? Need to prove. So the proof is very easy because it is finite dimensional. So here is injective, right? So you just make this basis to the basis on V. Okay. And then Surjectivity, also basis to basis. Okay, but then you realize that, it's exact at V, so meaning what? The kernel of that map is equal to the image of the previous map. So meaning every basis that you map from U to V, right? Those are the basis for your kernel. Okay, and then the surjective part is the basis for all the rest that's not in the kernel. Yeah, and then you have the kernel and the image put together is the V. Okay, does it make sense? So this is the good thing about vector space, finite dimensional vector space. Instead of talking about infinite set, right? You just talk about basis. Okay, basis, and then basis is finite. What's going on? This school every day got problem. Okay, good. Okay, then we can define something called the Euler characteristics. Okay, I'm not sure you take graph theory before, no? Graph theory did Euler characteristic, or maybe you didn't call it that name. V minus E plus F equals to 2, right? Huh? Yeah, so that's one of the Euler characteristic. That's the Euler characteristic for your graph, planar graph. So, so we could define it in general. So the Euler characteristic of V, okay, is the integer. Let's call it chi. What you do is you take the alternating sum of a dimension Vi. Okay. So that's why you have a V minus E plus F. There's an alternating sum there, plus minus plus. And then those represent a different dimensional stuff because the V is 0-dimensional, E is 1-dimensional, and then your faces is like 2-dimensional. V0, V1, V2. Does that make sense? Okay. And this obviously produce a number for you because these are integer. I mean, yeah, integer because you got minus sign. Yeah. And yes, V is a good change. Yes. Yes. Otherwise, I don't have VI. I need a sequence of VI. Okay. Proposition here is instead of so what can you imagine from this Euler characteristic? Because it's considering dimension of Vi, right? But then you notice that in the chain complexes, right, they are image of Di plus 1 is in the kernel of Di, right? So these dimension would be like overlapping. Okay, so you can imagine that there are some cancellation there. Can you imagine or not? Huh? I'll try give some examples. Can you imagine? Can you imagine? Cannot. Okay, let me think how to motivate. Okay, so if you look at the previous proposition, 有什么问题呢？ Okay, so if you imagine here, yeah, maybe. So let's use this to imagine that. Maybe this dimension V is, let's say, dimension 4. Okay, so you have some dimension 2 inject into it, and then maybe you subject to another dimensional 2 stuff, right? So what's the Euler characteristic for this? What's the Euler characteristic of this? You put the plus here, right? Then minus here, and then plus here. 0? So you get a 0. Does it make sense? Okay. Okay. Yes. Exact 吗？没有，没有，不要 exact。什么？对，很好的问题，很好的问题，那问题，其他人想着 exact 的 complex 是不是给你 Euler characteristic？
那个 sum 是不是从 minus 1到
Yeah, yeah, definitely. Yes. 整个 sequence
需要考虑那个 sum 那个
convergence 啊，convergence 的问题。那它就会算去 infinity 哦 ，maybe。exact sequence 啊？为什么你会这样问呢？不然你想一下，为什么你会这样想？
这个 example 就告诉我，
你说说看，引导一下他们想。
我只会相对一个单词一个字，中间那个会等于它变成两个加起来的单位。那这样子的话，如果用两边那个减掉中间那个，
那更长的 exact sequence。
更长的 exact sequence 就是，就我看到这边有一个 alternating 的概念，然后很难解释，但是这个从这个阴谋这边说，有卡，
有可能。其他的呢？
这个是对的。
对，我们要 proof。有问题吗？I mean like，知道他在讲我，知道在问他，你讲啊，你刚才讲嘛，你怎么会有这个 idea？你要去表达一下你这个 idea，你要来把它变成合理的怀疑，不会乱怀疑，你要有一个合理的怀疑。一定有一个逻辑在。
比方说 exact 可能等于，可能等于就相当于是，
跟它的 vi 本身的那个 dimension 有关系，它一定是 part of 那个 vi 的 dimension。
就相当于你前面那个送到的单位，你再过去一次，就等于它最后切掉。就是前面那个就是前面 fix 这个 map， 然后前面那个地方送过来的 dimension， 就正好等于我再送过去又切掉的 dimension。因为在这个点，它一进一出正好清掉这个在。
这是第一那边出3个啊，什么？为了这边今天那边去的话，那边出了3个，就切掉那个1就剩3个。或者4个吧，
那个要 depend on 你下一个 map 是谁来定的，你懂我意思吗？它 depend on 下一个 map 是谁决定，你才可以切了过后1才是3，可能你出去的是2。
意思就是你送进来2个map，你送出去的时候一定也切掉了2个map，
它只引来前面一个吧，没有引来后面。
前面一个而已，没有引来后面那个是。
剩下来的东西一定是 match 去对面的，只是保证你那
送
个
进来的东西被切掉。
剩下的东西被切
比如说你送进来两个代表，你送出去的时候一定被这两个代表一定被消掉，而且消掉的就是
因为如果不 exact 的话 ，meaning 什么？你的 image 只是 subset of 你的 so maybe 你有 two dimensional 的东西 map 进来，but then 可能就一 dimensional 被你切掉了。他的意思是说2的 map 进去，那个2的一定是被切掉，因为它 exact。你那个要去删的话，你要去下一个 exact 的 subjectivity 嘛，你还记得那个 injectivity 跟 subjective 的那个 exact 的位置不一样。Okay, so I think enough discussion. Maybe I can show you one statement here. Okay. Instead of calculating Okay, so okay. So instead of calculating VI, right, for all the VI, instead you can use this. You can use the homology to do it. Okay, so you can just consider the alternating sum of dimension of HI. Okay, so let's say this one we only consider finitely many terms, bounded complex. Okay, let's talk about bounded complex. Otherwise, we need to deal with infinite term. So in this case, in particular, if V is exact, then from here we can see that the Euler characteristic should be 0. 因为它 bounded 了嘛，反正你就是从底量到高啊。bounded, yeah, bounded. Yeah, let's assume this is bounded case. Okay, bounded meaning it's only appearing for finitely many terms. 不 bounded 啊 I guess 成立耶，只是说not sure how you do induction. 应该成立。I mean this proof is not too hard, but then you need to write down. Should we prove this now or next time? 其实还有4分钟。其实不太难。
超过天，
OK， 超过条。
然后
啊？
然后天。
OK， 等一下，不然我直接 show proof 给你们看。
啊？现在这个开讲。
Yeah， 不会难其实。OK。So actually we prove by induction. Okay. If you can see the n equals to 1 case, which means 2 terms complex, then you can do the rest already. Okay. So in this case here, let's look at the n equals to 1 case. Okay. So we want to show that this term here, dimension v0 minus dimension v1 is equals to the dimension of h1.在这边 basically dimension of h0 v1 minus dimension of h1 v the complex h1 of that complex. So basically, what do? You just write down the definition of homology. So what's the homology? So it's dimension of kernel of alpha 0 minus dimension of image of alpha 1, and then the other one is dimension of alpha 1 minus dimension of alpha 1. Yeah, image of alpha 1. Okay? Wait, let me think. 好像有东西有问题。So this one is 0跟1 and then this one should be 1 and 1 and this one, let's see. What's that? 2 啦，这个 alpha 2 Can you see the increasing number? Can you see the increasing number? 0, 1, and 1, 2. Okay. But then alpha 2, what is alpha 2, right? In this case here. Alpha 2 is actually a 0 map. Okay, alpha 2 is a 0 map. So so then meaning how these three terms here relate to these two terms. And how these three terms here relate to these two terms here. Well, I rearrange them. Okay, how do I rearrange them? So I rearrange this dimension kernel of alpha 1 with the dimension of image of alpha 1 together. And then I arrange dimension of kernel of alpha 0 with the dimension of image of alpha 0 together. But then this thing is 0 because image of alpha 0 is 0. Okay, so now then I need to argue to you know why this two dimension add up to be a dimension of V0. Why this two dimension add up to be a dimension of V1. Okay. Well, this is what is the setting we have here? We have finite dimensional module, is it? What's our setting here? Just finite dimensional vector space, right? So for finite dimensional vector space, right? If I give you a map, okay, if I give you a linear map, you can split it into the kernel part and the image part. Okay, you know how to do it? Because the kernel and the image are the subspace. Okay, subspace has basis. Okay, and their basis should be no overlap. Okay, okay, and then the others you just prove by induction. Okay, prove by induction. I suppose you can for the n and then you can do n plus 1. Okay. Okay. Okay, then let me see. Is it worth to continue a bit? Okay, maybe next part we will do something higher, more advanced things, which we call the quadratic group. Okay, quadratic group of this category here. Huh? Yeah, so what's this quadratic group? Quadratic group of this finite dimensional vector space category here. It is a free abelian group on the isomorphism classes. Okay, how do we determine this isomorphism classes then? Basically, you need to have a short exact sequence first. Okay, you need to have a short exact sequence like this V. So if there's any V that can fit into the short exact sequence, they are fall into the same isomorphism classes. Okay, so meaning you have a have a short exact sequence, take this middle guy, be the representative. 确定这是 quadratic 提出来的，不知道它讲的是 quadratic 的。This is a higher dimensional Euler characteristic. So we also can define something like this. Instead of putting a dimension there, okay, we will put a vector space there. Yeah, the isomorphism class. 出来是一个 vector space. It's something in the what's the space? Sorry, what's the space K? This space is this. I call it a quotient. Quotient. Yeah, quotient. Yeah, because F here is a free abelian group. I think this notation is what Siyu used last time, right? For the free abelian group. So it's generated by these, generated by the finite dimensional vector space, and then I quotient out by this. Wait. On my way prove this property. And then this is actually a higher dimensional Euler characteristic. 再重新讲过，你可以叫 Adrian 来，下次叫他来听课，叫 Adrian 来啊？有，跟我的研究有关。这样子 ，OK， we can continue this again. But then this you can see that we can define this chi again. But then this chi here is no longer dimensional of vi, but then we replace it by the isomorphism classes of vector space. A bit like, did you know the characteristic polynomial of a matrix? So instead of putting X there, you are putting a matrix there. Okay. It's not crazy lah, but then it's very interesting stuff. Yeah. Maybe later on we can mention a bit on my research that uses these things. Maybe we can tell you a little bit. This can work as an invariant of objects, mathematical objects, like Knox invariant. There's a Knox invariant called John's polynomial. Okay, then we can realize this John's polynomial as these dimension of some vector space. Okay, maybe we can talk more next time about